lecture on stoichiometry is from unit number 11, objective number 5, which says you will solve stoichiometry problems involving mass using molar mass and molar ratios. So really, objective number 5 also includes objective number 3 and 4, which say you will calculate the molar mass of chemical compounds and you will construct mole ratios from balanced chemical equations and apply those ratios in stoichiometric calculations. So objective number 5 really includes objectives 3 and 4 as well. So far you have done mole-mole stoichiometry, which means you've started with a balanced equation and you have recognized that the coefficients in a balanced equation represent mole ratios. So what that means is, for example, in this equation of nitrogen and ammonia turning into, or nitrogen and hydrogen turning into ammonia, the ratio of 1 to 3 to 2 means that you need 1 mole of nitrogen gas to react with 3 moles of nitrogen gas to make 2 moles of ammonia. So if instead you were to use, start with 2 moles of nitrogen, you would therefore need 6 moles of hydrogen, and that would make 4 moles of ammonia. Conversely, if you only had half of a mole of nitrogen, you would need 1.5 moles of hydrogen, and that would make 1 mole of ammonia. So it's pretty simple to do the mole-mole stoichiometry because it's just you're very straightforward, just using the coefficients to help you predict the quantities of the other chemicals in that equation. So here's a problem using that mole-mole stoichiometry that you've already worked with, and it says how many moles of N2 are needed to react with 42 moles of hydrogen. So sometimes, as these problems are going to start to get more complex, it's helpful to look at the problem and identify what you're starting with, what quantity you're starting with, which is right here, 42 moles of hydrogen. And I'm going to recommend that you write that down underneath the quantity, underneath that substance. So 42.0 moles of hydrogen. So I'm going to put that with its unit underneath the hydrogen. Then the next thing that you'll want to do is in the problem recognize what substance are you trying to find and what unit are you trying to find. So here, how many moles of N2? So it's N2 that you're trying to find. So I'm going to put X moles underneath nitrogen. So in all of these problems, now that we know that we're starting with the amount of hydrogen, we're trying to find the amount of nitrogen, ammonia doesn't factor into this at all, so we don't really need to concern ourselves with that quantity for this particular problem. With all these stoichiometry problems, I recommend that you start with the quantity that you are given. 42.0 moles. Notice that I have included all the significant figures. I have included the unit, but I'm also going to make sure that I include the substance. Okay, there are 3 substances in this equation. If you don't indicate which substance you're starting with, you really have nothing. You're not really communicating your work in this problem. So start with the quantity that you're given, and this is we're going to set this up as a conversion problem, which means you'll set up a conversion fraction. So we're going to multiply by a fraction that's equivalent to 1. And in all of these conversion problems, the first thing you do is the unit that you started with, in this case moles of H2, immediately you should put that unit down in the denominator because we want to get rid of that unit, we want it to cancel. In the numerator, we want to put the unit we're trying to solve for, which is nitrogen. So what we can see here is we now have blank spaces where we need to put the numbers into this conversion fraction. We need a number here and we need a number here. Well, as you remember, these numbers come from the balanced equation. So the coefficient in front of the nitrogen is a 1. That's this one right here. And the coefficient in front of the hydrogen is a 3. This 3 right here. So now, the purpose of doing this is it communicates that you recognize that moles over moles of hydrogen will cancel. You're left with a unit of moles of nitrogen. So we know that our answer will be moles of nitrogen. And what this does is this sets this up so that anything in the numerator of these fractions you'll be multiplying by. So in this case, you'll be multiplying 42 times 1. And anything in the denominator of these fractions, well, you'll be dividing by that number. So in this case, it's 42.0 divided by 3. And of course that comes out to 14.0. Notice that I am maintaining the number of significant figures that I had to start with. I had 3 significant figures in 42.0, so I will end up with 14.0, 3 significant figures in my final answer. Okay. All right, let's take a look at the second problem, because now, what if you are given grams of one compound, and you have to find grams of a different compound? And a gram, this is what's called gram-gram stoichiometry, because you're starting in a quantity of grams, and you're going to end up in a quantity of grams. But this problem, you can't start out by using the coefficients in the balanced equation, because the coefficients in a balanced equation do not represent a mass ratio. So you have to break this down. The substance that you are given, first, you'll take that grams quantity of the given compound and you have to convert it to moles. You'll do that by using the molar mass of that substance. So that will be one conversion fraction. The purpose of this is you will convert grams to moles of the original substance. Once you have moles of the original substance, you can convert it to moles of the destination substance, the substance you're trying to figure out the quantity for. So in this case, you'll be going from moles of one substance to moles of the other substance, and this is just like what we've done so far, the mole-mole ratio. And so to do that, you will use the coefficients from the balanced equation. So this middle conversion fraction is just like what we were doing in mole-mole stoichiometry. If you leave the problem here, you'll have your answer in moles of the compound of interest, but most oftentimes you're going to be asked to convert this quantity into grams of that new substance. And so what you'll have to do is you'll take moles of this new substance and you'll have to convert it back to grams of the new substance using the molar mass from the periodic table. Okay? And you'll have to, so it's essentially 2 molar mass problems surrounding a mole ratio problem. And the reason why we have to do 2 molar mass conversion steps is because the 2 compounds will have 2 different molar masses. They don't weigh the same. So gram-gram stoichiometry is going to end up having 3 conversion fractions. And let's take a look. If you completely combust 56.0 grams of ethylene, which is C2H4, how many grams of oxygen will be used? So we have an equation here. It appears to be balanced, and this is always something you should check first. If the equation's not balanced, you will have to balance the equation before you proceed to the stoichiometry problem. So we see here that this is a balanced equation. So what I'd like you to do is make sure you identify the quantity that you're starting with. 56.0 grams of ethylene. So I'm going to put that quantity, 56.0 grams, underneath the ethylene molecule. So I know that I'm starting with 56.0 grams of this substance. I'm trying to determine grams of oxygen. So I'm going to put X grams underneath this oxygen. So these are the only 2 substances involved in this particular problem. So for this problem, we're going to pay no attention to the products. We're just focusing on those 2 reactants. So to start this problem, remember stoichiometry problems, you will always start with the quantity that you are given, 56.0 grams of C2H4. Now notice when I started with this quantity, I maintained the number of significant figures of 56.0, 3 sig figs. I've included the unit, in this case it's grams, and I've included the identity of the substance we're starting with, C2H4 ethylene. All right, so what we'll see here, first fraction is meant to convert grams of C2H4 into moles of C2H4. So immediately, the first conversion fraction, go right to the denominator and put the unit that you started with in that denominator. Now remember, this first fraction is meant to convert grams to moles. Okay, that's what we're doing here. So of the same substance. So really, we're just staying in the same substance, C2H4, going from grams to moles. So to do this, this is molar mass, and we need to get that from the periodic table. Right? Remember, it's always 1 mole of the substance weighs a certain number of grams. So 2 carbons, each at 12, adds up to 24, plus 4 hydrogens adds up to 28. And to the nearest tenth, as I always recommend you do for molar masses, it is 28.0 grams. Now we're not going to do any math yet. We're going to set up the entire problem and then do the calculation as a chain calculation, as one right after the other, without any intermediate answers. If we left the problem here, grams of C2H4 would cancel. We are now in the unit of moles of C2H4. So with conversion problems, we're now trying to get rid of moles of C2H4 because remember, our destination is we're trying to get grams of O2, and we're not there yet, so we can't stop. So let's get rid of the moles of C2H4. Immediately put that into the denominator of the second fraction. The second fraction, the job here is that we're going to go from moles of one substance to moles of the second substance. And so for this equation, you will use the coefficients from the balanced equation. So here's where we get the chance to convert moles of C2H4 to moles of the destination compound, the compound we're trying to solve for, which in this problem is oxygen. So moles of O2 is going to go in the numerator. Now the numbers that will go in this fraction are the coefficients from the balanced equation. So in front of the oxygen I see a 3. And in front of the ethylene, there is no number, so that's assumed to be a 1. If I left this problem here, I would see that moles of C2H4 would cancel with moles of C2H4, leaving us within the unit of moles of O2. But we're not trying to get to moles, we're trying to get to grams. So hence we need one more fraction. And since we're trying to get rid of this unit of moles of O2, I'm going to put that in the denominator of the third fraction. So this fraction, we're going to take moles of this substance and we're going to convert it to grams of this substance. And again, this is going to be a molar mass conversion. So moles to grams, moles of O2 to grams of O2. In molar mass conversions, you're always seeking the mass of 1 mole of that substance. So 1 mole of O2, from the periodic table, each oxygen is 16.0. So the molar mass of O2 is 32.0. All right, moles of O2 will cancel with moles of O2, and now we are ready to plug this into our calculator. Remember, you're going to start with a 56.0 in your calculator. Anything in the top, in the numerator of all these fractions, you will multiply by. So go ahead and you can multiply by 56 times 1 times 3 times 32. Hit the equals button, and you'll divide by everything that's in the denominator. Well, the only number that's in the denominator that we really have to divide by is 28.0. Your final answer should be rounded to 3 sig figs because that's the number of sig figs we started with in 56.0. And you should get a final answer to be 192 grams of O2. All right, let's try another problem. How many grams of gold chloride can be made from 100.0 grams of chlorine gas by this reaction? So we see here we're trying to find how many grams of AuCl. So I'm going to put X grams underneath the AuCl of this equation. And I'm going to start with 100 grams of chlorine gas. So I'm going to find the chlorine gas in the equation and write 100.0 grams underneath it. So for this equation, we're not going to do anything with the Au. And so here we're going to start with the quantity given, 100.0 grams. Notice I maintain the number of significant figures, I included the unit, and I'm also going to include the identity of the substance I'm starting with. This is a grams to grams problem. Anytime you have a grams to grams problem, there is going to be 3 conversion fractions. Okay. The first conversion fraction will get rid of grams of chlorine gas, so GCl2 in the denominator, to moles of Cl2. So the first fraction is a molar mass problem of the original substance, converting that substance to moles. 1 mole of chlorine gas from the periodic table, if we add it up, works out to 71.0 grams. If we left the problem here, grams of chlorine gas would cancel, leaving us with moles of chlorine. But now, that's not what we're seeking. We are seeking grams of gold chloride. So we have to keep going. Now, right now we are in moles of Cl2, so now we're going to need to use the 3:2 ratio to help us convert to moles of gold chloride. So moles of Cl2 needs to go immediately into the denominator, so they'll cancel. And on the top, we're going to write moles of the compound we are interested in converting to, which is AuCl3. The numbers that go into this fraction are the coefficients from the balanced equation, 2 AuCl3 and 3 Cl2s. If we left the problem here, moles of chlorine would cancel with moles of chlorine, leaving us with moles of AuCl3. But we don't want to be in moles of AuCl3, we want to be in grams of AuCl3. So to do that, we will put moles of AuCl3 in the denominator and grams of AuCl3 in the numerator. Molar mass is always the quantity. 1 mole of the substance is equal to the molar masses added up on the periodic table. If you take a moment to add up those molar masses, it is 303.5 grams in 1 mole of AuCl3. If we leave the problem here, moles of AuCl3 will cancel, and your final unit will be in grams of AuCl3. And in your calculator, 100 times 1 times 2 times 303.5. Hit the equals button in your calculator, and then you will divide by 71.0, hit the equal sign, divide by 3 again. And then, of course, dividing by 1 doesn't change a thing, so that's not a necessary step in your calculator. If you've done the key stroking and the inputting of your numbers correctly, you should end up with a number, an answer to 4 significant figures, because our original number was 4 significant figures, to be 284.8 grams of AuCl3. One last problem. Now this is more typical of word problems that you'll find. Here we're going to give you a little story about the reaction. Although mixtures of hydrogen and oxygen are highly explosive, pure elemental hydrogen gas itself burns quietly in air with a pale blue flame, producing water vapor. The problem goes on to say, calculate the mass in grams of water vapor produced when 56.0 grams of pure hydrogen gas burns in air. All right, this first sentence is essentially fluff. This is not information that you need to do this problem. It just gives you a little backstory on this equation. It's kind of interesting, but it doesn't make any impact on the problem itself. So reading the second sentence, what are we trying to find? It says to calculate the mass of water vapor. So X grams of H2O is what we're trying to find. The quantity we are starting with is 56.0 grams of pure hydrogen gas. So I'm going to put that quantity underneath that substance. So for this equation, we're not doing anything with the oxygen. All of these stoichiometry problems, you will begin with the quantity that you are given. 56.0 grams of H2. Again, notice that I wrote down all 3 significant figures, 56.0. I included the unit, and I included the identity of the substance, so grams of H2. The first fraction, grams of H2 will go in the denominator. Moles of H2 will go in the numerator, because remember, the first conversion factor, you are trying to convert grams to moles of this first substance. 1 mole of H2 added from the periodic table is 2.0 grams of hydrogen. We'll leave the problem here. Grams of H2 will cancel. The second fraction, moles of H2 immediately goes on the denominator, so it will cancel. Now here's the second fraction, the mole to mole fraction allows you to convert from moles of the original substance, in this case hydrogen, into moles of the desired substance, in this case water. The numbers that go in the mole-mole fraction come from the balanced equation, so 2 to 2. If we leave the problem here, moles of H2 will cancel with moles of H2, leaving us with a unit of moles of H2O. But we're trying to find grams of H2O, so we need to do one more step. Moles of H2O is going to go in the denominator. Grams of H2O is going to go in the numerator. 1 mole of water from the periodic table is 18.0. This conversion fraction allows us to cancel out moles of water, leaving us with a unit of grams of H2O, which is what we were seeking. In your calculator, 56.0 times 1, which of course is still 56.0, times 2 times 18. Hit the equals button. Divide your answer by 2. Hit the equals button. Divide that answer by 2. And of course, dividing by 1 in the end doesn't change a thing. So in the end, 3 significant figures is where we started, so our final answer should be rounded to 3 significant figures. And if you've done this correctly, you should have the number 504 grams of water. So there it is, mole-mole stoichiometry. You should now have a second problem set to try some of these problems on your own. You'll find in the second problem set that you will first have to balance the equations before you can begin the stoichiometry problem. So you'll need to get that from your teacher, and that's where I will see you in the classroom.